3313. We have monochromatic light, 75 watts. We have a wavelength which I believe has nothing to do with the problem, 500 nanometers, and it radiates uniformly in all directions. And the question now is, what is the associated E0 and B0, the amplitudes of the E vector and the B vector, if I am at a distance r from this source, light source, of about 3 meters. Now in what follows, I'm going to pretend that I can represent this radiating source, which radiates, I hate to use that word, but it radiates photons in all directions. I pretend that it can be represented by a plane electromagnetic wave described in the way we just did, with a uniquely defined E vector and B vector, except that now it doesn't go in one direction, but it goes out spherically. And when I do that, I have here this source which has a certain energy per second, 75 watts. I call that the luminosity, because I'm an astronomer and astronomers call that luminosity. And let me put around this source at radius r a sphere. And let me put here a little surface element on the sphere. Then there will be an energy flux flowing through this little surface element, which is perpendicular to this direction of r. This element A, this little element dA, whatever you want to call it, is perpendicular to this flux. It's in the same direction that the radiation is going. So L is luminosity, which is always in joules per second. That means in watts. F is energy flux, which is joules per second per square meter. And so therefore, if there is no absorption between the source and this sphere could be huge, could be 10 meters, could be 10 light years. But all the energy must come out of that sphere if there is no absorption between the source of electromagnetic radiation and the sphere with radius r. So it follows immediately, if there is no absorption, that 4 pi r squared times F equals L. But F, as you will see, is exactly what we have called in the past the mean Poynting vector. I say mean because if we take plane wave solutions to Maxwell's equations, then of course we have cosine terms, and if we have cosine terms we have to take the mean values. And so the mean value of the Poynting vector, which equals the mean value of E cross B divided by mu 0, then also equals L divided by 4 pi r squared. And you see immediately, which is no surprise of course, that the Poynting vector falls off as 1 over r squared. The farther you are away, the smaller the flux, and it goes as 1 over r squared. The luminosity, the amount of energy that comes out here, of course, is independent of r. So let us pursue this a little bit. Notice, by the way, that the Poynting vector is completely independent of the wavelength lambda. So if now you are being asked what is the E0 and what is the B0, you effectively have to use this equation. We know that the Poynting vector, the mean Poynting vector S, is the mean value of this quantity. Well, the mean value of that quantity equals 1/2 E0 squared divided by mu 0 times C. Remember, the 1/2 comes from the fact that you're going to get a cosine square term in here, because this has a cosine dependence of time and this has a cosine dependence of time. They're perpendicular to each other, so I can forget the cross. But B0 is also E0 divided by C, so that's why I get this C here. And that now equals L divided by 4 pi r squared. And you see, you know everything that there has to be known. You know L, you know R, mu0 and C, so out pops E0, and if you have E0, out pops B0. And so the E0 and the B0 only depend on L and R, they only depend on the Poynting vector, and they are independent of the wavelength. And since the Poynting vector falls off as 1 over R squared, you see that E0 falls off as 1 over R, and B0 also falls off as 1 over R. Let us take the sun. The sun is a very powerful source. It has a luminosity of 4 times 10 to the 6 watts. And the distance, d, from the sun to the Earth is 150 million kilometers. Being an astrophysicist, I just happen to remember that. When you apply the above, you will find that E0 is about 1,000 volts per meter at the distance of the Earth, and that B0 seems significantly small, 3.4 times 10 to the minus 6 Tesla. The reason being that you have to divide this by C. And the mean value of the Poynting vector, which is the luminosity of the sun, divided by 4 pi r squared, is the famous number 1.4 times 10 to the 3 watts per square meter. And this number, I will come back to, is very important. It's a little bit more than 1 kilowatts per square meter. And what does that mean? It means that the amount of energy from the sun that reaches the Earth for every square meter in the direction perpendicular to the radiation is a little more than 1 kilowatt per square meter. 1,000 joules per second. If you ever want to harvest solar energy, this is the maximum you can ever get. And I will get back to that, and you will see the consequences of that. The consequences of that are, as I will show you, that to harvest solar energy is by no means a trivial matter.